Good to go, Caitlin.
Yeah?
Yep.
Okay. All right, we'll go ahead and get started here. Thank you all for joining us today, both online and in person.
I can't see you because John's in the way.
Both online and in
Thank
person. Today's guest presenters are from just down the road, National Weather Service, Milwaukee Sullivan Weather Forecast Office. We've got 3 of their outstanding meteorologists here today. We've got our double UW-Madison AOS alum, Andrew Quigley.
Everybody.
Kevin Wagner and Cameron Miller. And collectively they worked on this historic event for a couple of tornadoes that occurred across southern Wisconsin earlier this year, and they're here to tell us all about it. So.
Cam, the floor is yours.
Yes. All right. So, yeah, thank you, Caitlin, for that wonderful introduction here. So we're going to be talking about the historic event that happened on February 8th with the tornadoes that we had, the very first in the month of February for Wisconsin here. We're going to be going through the forecast leading up to it, some of the messaging that we did, and then the warning phase that we went through here. So, again, an overview, we'll go through that. Talk about the buildup. We had a little bit of forecast concerns leading up to the event, so we'll cover that. And we had a little bit of pre-event messaging, but we won't go over that too much today. We'll talk about the morning forecast ifs and how we handled those. And then Andrew's going to be taking care of the afternoon meso-analysis and talking about how the ifs kind of got toppled on our way towards that event. And then pivoting the forecast message in the afternoon. And then Kevin Wagner's going to be taking the warning operator's perspective because he was the one that was issuing the warnings during that particular event. So here's a quick recap. We had 2 tornadoes that day of particular significance. We had the Albany, Wisconsin tornado with 110 miles per hour peak winds there, path length of 8 miles in length. And it ended up being an EF1. And then we had the Evansville to Lake Koshkonong tornado, a peak wind of 130 miles per hour and a path length of 26.2 miles per hour, or not miles per hour, miles. And as some of you know, that's the length of a full marathon, so luckily for Fort Atkinson up here, the tornado's legs got tired and just stopped running before it got to Fort Atkinson. So.
Told you you'd get a few chuckles.
There we go. All right.
You're talking about it the way over.
Yeah, I was leading up to that joke the whole time. Anyways, so here are a couple pictures of those particular tornadoes. We had a couple chasers on those. So here's one from Tom Purdy of the Albany tornado, and then a beautiful backlit picture of the Evansville to Lake Koshkonong tornado there by that lightning there, and then on the horizon outside of the subdivision out there as well. So one of the things that we talked about with this particular event was the odds, okay? So, you know, what are the odds of seeing this particular tornado event in the state of Wisconsin during February? So going over some of the odds that we're trying to compare this with here. The odds of being struck by lightning in your lifetime is around 1 in 15,000. If being dealt a royal flush in poker, that's around 1 in 500,000, or the odds of being injured by a bear in a national park visit, that's around 1 in 2.7 million, okay? So the forecasting challenge here is communicating that less than 0.01% risk here, because if you look at the tornado climatology, we have a nice blob here on Dixie Alley in the south in February here. And not much going on here up in Wisconsin. So looking at Climo, there's a less than 0.1% chance, 1 in 1,000 chance of seeing a tornado in southern Wisconsin during the first week of February. But if you were to extrapolate it out, taking a look at some of those contours and doing a little bit of back of the envelope math here, seeing a tornado in the month of February in Wisconsin is close to a 1 in 10,000 chance to a 1 in 10 million chance there. So there's a wide area of variation there. There's a lot of small chances that just came together that day, and really all out is to see this event here. So we were trying to communicate that less than 0.01% risk there on that particular day. And just a little bit more of a historical context here. There were no tornado warnings in Wisconsin, or no tornadoes in the state of Wisconsin during the month of February. So that whole recorded history that we have of keeping track of tornadoes and tornado warnings from 1950 to 2023, we basically did not see any tornadoes or tornado warnings in the state of Wisconsin during the month of February here. So looking at February severe warnings here, we had 9 in 1999, 4 in 2008, and 3 in 2017. So on the particular day that we had this past year, on February 8th, we actually issued 8 severe thunderstorm warnings and 5 tornado warnings on that particular day. So we basically blew that historical context out of the water. And just looking at other months in winter here, we also did record tornadoes in January and March as well. Okay, so February was kind of that odd month out where we hadn't seen any tornadoes at all because we're in the dead of winter. And overall, it was a weird winter overall. We had the warmest winter in Wisconsin by about 2.3 degrees, so it basically beat another really warm winter that we had in 2001 and 2002. We had the highest state high ever recorded in the season of winter down in Kenosha. That was 77 degrees. And in the north woods of Wisconsin, we actually had snow deficits approaching 60 inches. Okay, so we were well behind on snow for this particular winter here, and we were well above normal with temperatures. So when we go into February, there are some severe weather gotchas that kind of put a lid on our severe weather risks climatologically here in Wisconsin, okay? So the first one, obviously it's winter, but if we have some sort of warmer setup, usually a cool breeze will kind of put the kibosh on things, or we have something that we like to refer to as the cheddar curtain in our office. So we'll go over those here pretty quickly. So first off, it's winter. The climatological normals here are listed for Milwaukee and Madison. On this particular day, the typical high and low for Madison is 29 and 13 respectively. And on this particular day, February 8th here, Madison actually reached a high of 55. So we're basically blowing that climate normal out of the water. Usually in Madison too, you have an average snow depth of 3.9 to 9.8 inches of snow on the ground per no-risk data. But looking at our observed snow depth for that particular day here, there were basically, little to no snowpack on that particular day. And then looking at that cool or cold breeze that we usually get with our winter setups here, let's say we have this typical envelope of low pass that we get through Wisconsin here. Usually, if you have a digging trough over the central plains, the low path will kind of take either a flat path over basically northern Illinois, northern Indiana, or it can hook up into northern Wisconsin here. So if that low track is a little bit north and it goes towards northern Wisconsin, what will happen is synoptic flow will actually drive cold air in off the lake, and we'll get cold air at the surface, okay? So we might have some warm advection over this cold layer. You might get elevated storms, but surface weather, severe weather threats will suffer, okay? So you're not really looking at tornadoes in that situation. You might have some hail, but not really looking at tornadoes here. And then we have something else we like to call the cheddar curtain, okay? So if the low takes a more flat path over northern Illinois from west to east here, what will happen is synoptic flow will drive in cold air off of the lake, and the warm front in particular will get hung up along the Wisconsin-Illinois border. And this happens so typically that we call it the cheddar curtain, okay? And basically, again, severe weather threats that are tied to the surface will suffer, and storms will either ride along the warm front in northern Illinois, or they will cross the warm front in southern Wisconsin and promptly turn to mush because of the depth of the cold air. But on this particular day, on February 7th here, we're looking at the forecast for February 8th here. The low track is well outside of that typical envelope of tracks that we have for this particular event here. So we're looking at the 0Z February 7th HREF here, and you can see this whole area, you got a nice tongue of warm temperatures coming up here. The warm sector is stretching all the way up into northern Minnesota here. And we were basically kind of looking at these low paths and kind of trying to figure out where this low would go. There was a little bit of disagreement, but models were showing some weak cape and a potentially crashing cold front that would come through the area here. So at this particular juncture, we weren't sure about severe weather. We listed that in our AFD, but we wanted to make sure that people knew at least there would be a low-end threat for this particular event. And then going towards the event, and the February 7th afternoon forecast here, we got a new HREF, and now we're starting to see some hints that there might be something good going on for severe weather on February 8th here, okay? So the new HREF straightens out some of the details, but we have a few ifs here, okay? So we have that cold front coming through. We have large warm front over the northern Wisconsin into the UP here, but we also have sort of a secondary warm front that's poking up into the middle to upper Mississippi Valley here. We also noted that there was no lake breeze going on here. You can see the wind barbs are actually out of the south here, and we don't have a lake breeze being driven inland by that synoptic float here. Okay, so that's one thing that looks good for severe weather. We also have a strong 850 millibar knot, 50 knot jet here, and things are looking good for low-level kinematics in this particular environment. We also have at least a little bit of surface to 500 shear of 35 to 40 knots, which looks very good. And we have steep 700 to 500 lapse rates of around 7 to 8 Celsius per kilometer. And really good 0 to 1 kilometer SRH here. So the yellows and dark oranges here are 200 to 300 meters squared per second squared. But we have some ifs that we have to figure out here, okay? So we're looking at dew points here and some of the model disagreement. So the dew point, isohydrosotherm of 45 degrees is listed here, or shown here with the green line. And we also have some model differences between the HREF members here. Okay, so we have the AirW, the HER, and then the NAM nest over here, all showing different progressions of storms as we go into the afternoon here. So we're looking at all these different models and trying to figure out which one is going to be the best particular model here. We're trying to figure out if those dew points are going to be enough to support a surface weather event or surface-based severe weather event here. And we're also looking on the morning of the particular event here, we're looking at some morning convection. Usually in Wisconsin, we struggle with morning convection kind of ruining our severe weather events here. So we're trying to figure out if this particular morning convection will ruin surface-based severe weather in the afternoon here. And we also have some cloud cover. This is the ensemble mean cloud cover that is being realized here on the HREF model at 21Z on February 8th here. And we're trying to figure out if there's going to be any potential breaks here, okay? So we're trying to pin down if we get those dew points, if we get some breaks in the clouds, if we see instability. We already know that some of the kinematics are great. We're not getting a lake breeze in here, so we're trying to figure all this out moving into the event, and Quigley is going to cover how these ifs got toppled as we went into the afternoon on February 8th.
Thank you very much, Cam. Great job, by the way. You did a great job outlining that. So really, what we've been talking about to this point so far in the presentation is, A, why is something like this just so rare from a climatological standpoint? Why was the fact that we were even talking about tornadoes during the day on February 8th something that was just unheard of from a historical standpoint? And then really, we've kind of started to outline, as Cam did a really good job of some of the things that we were seeing in the forecast data 36, 24 hours ahead of this event that really kind of even have us saying if. And really, what all this boiled down to was two questions going into February 8th. Were we going to get too much rainfall in the morning hours to dampen any chances for thunderstorms during the afternoon? And then two, was our cloud cover going to just be too much? Were we going to have too much in the way of clouds to really keep our surface temperatures down, which also would go against the thunderstorm chances? So those are really the two questions that we walked into February 8th with. And as we kind of went through the morning hours, through about lunchtime, it became very clear, based off some things we were seeing in the OBS, the satellite, that this might, in fact, actually come together by the late afternoon of February 8th. And really, our reaction, we weren't bunking beds or we weren't wearing night vision goggles, but it looked a lot like Step Brothers when Dale and Brennan realized they just became best friends. And we kind of very quickly had to ramp up our messaging, kind of pivot, and get the public ready for truly what was something that was about to be unprecedented. So I talk about some of the things we were looking at, and satellite, really, as we went through the morning hours, mid to late morning hours, specifically on February 8th, was one of the very telling things that we were looking at and was starting to make us concerned. And really, we're showing you the visible satellite imagery here between 14 and 17Z on February 8th. And you can see regionally we have cloud cover, but we don't really have a uniform overcast deck of clouds across our area that we were thinking might be around during the first half of the day on February 8th. And this is really apparent over southeast Wisconsin there, from Sheboygan down through Milwaukee towards Kenosha, where really we spent the entire half of the morning hours on February basically in mostly sunny skies, which was definitely a surprise and went a little bit against the expectations that we had going into that day. But even back towards southwestern and south central Wisconsin, here in Madison, where we eventually had the tornadoes just a little south of here, you can see that we had cloud cover, but it wasn't really uniform, like I was saying. It wasn't uniformly overcast. There were breaks between those clouds. There were high clouds allowing for filtered sunshine to break through. And unsurprisingly, if we move over to our surface observations here, showing you between 14 and 18 Z on February 8th, you can see that over southeast Wisconsin, temperatures soared into the low to mid half of the 50s by about lunchtime on February 8th. So that's about 30 degrees, 35 degrees above normal for the first week of February. But even closer to the tornadoes over southwestern Wisconsin, where we were getting those breaks in the clouds, getting that filtered sunshine, we had temperatures by lunchtime get into, for example, the lower part of the 50s right here in the Madison area. We got to about 55 in Janesville, and the lower half of the 50s in Platteville as well. So that was alarm bell number one to us that really started to clue us into the fact that this might actually happen going into the afternoon. You take these trends that we were seeing in the clouds, and then you add in the fact that our radar through the late morning hours on February 8th looked a little bit like this, and then we really started to get concerned. We were maybe thinking through mid to late morning on February 8th that we would have a pretty wide kind of spread shield of rainfall coming through and a wing of warm air advection that we had coming in. And we were thinking that that could really hold our temps back into the upper part of the 40s, which would effectively shoot any severe potential in the foot. But as you can see, we really had kind of this weak little band of precip from Green Bay down to Janesville here. That wasn't reaching the ground, that was just elevated virga. But then further to the west, say from Wapaka down to Monroe, we did have scattered, isolated kind of shower activity, but it was very hit and miss in nature, and it really wasn't long lasting at any one particular location. So we had underperforming cloud cover, which was bringing those surface temps up. We weren't really getting the rainfall that we were expecting. And then you add in the fact that to our west, behind all of that in Iowa, we're always looking upstream when we're trying to forecast near term. You can see that behind of all of this that we had going on, we had mostly sunny skies and basically uninterrupted surface heating working in from northeast Iowa, southwest Wisconsin. And really, you can see the impact of that in action as we get into the afternoon hours on February 8th, now showing you 18 to 21 Z on the surface ops. And you can see the combined effect really in action over southwest Wisconsin of the lack of earlier day clouds, lack of earlier day rain, and the clearing skies moving in from the west with surface temps getting up into the upper half of the 50s and even a few locations in Grant County, as well as the Wisconsin River Valley, briefly hitting 60 degrees that afternoon. So that was a cause for concern for us because we knew since the two questions regarding cloud cover and rainfall, we knew that basically both of those were going to suffice and fall into place favorably for severe weather potential. We knew it was time to kind of start raising the alarm bells as an office. And we knew that with that sunshine that we were going to have around, we were going to have a very favorable near storm environment in place for not just severe thunderstorms, but possibly tornadoes. So in the next few slides, we're going to walk through that near storm environment. We're going to show you some images, some animations. But what we've actually done for you guys here in the audience is we actually have an interactive near storm environment prepped for you as well. So what you can do is you can go ahead, scan that QR code, and you'll get into this environment that's got an assortment of different variables there for you, a couple different time steps. You can also overlay those variables with our tornado paths that we had that day, kind of see how those paths aligned with those sorts of things, just to kind of give you a more interactive look at what the atmosphere looked like on February 8th while we present. So we'll jump right in on that. And we'll kind of briefly talk about how we approach these situations as forecasters. And we'd all agree when we're kind of diagnosing a severe weather setup, we like to take what we call a top-down approach or almost a funneled approach. So we like to start at the synoptic level. We like to diagnose what's going on the broad scale to give us favorable upward vertical motion across the region. And then we'll start to drill into the more fine scale details like the mesoscale things, even storm scale as you get deeper into an event. And starting on the synoptic scale, particularly in the mid-levels of the atmosphere, we're showing you here at 12, 15, 18, and 23 Z on February 8th, the 500 millibar heights that we had in place there in black, the vorticity and the color fill, and then positive vorticity advection within that 700 to 400 millibar layer. And really, you could see the key feature of the day on February 8th was this upper low pressure area of troughing that we had in the northern plains early in the day that eventually kind of worked and dug into the upper Mississippi Valley by early evening and the time that we were seeing thunderstorms in our area. You can see, unsurprisingly, due to the curvature and the flow going around that upper wave, we had plenty of vorticity that was coming through that base and really over southern Wisconsin. And that's a favorable setup for positive vorticity advection through the mid part of the atmosphere and upward vertical motion. So operationally, we're looking at this and we know that we're going to have plenty of mid-level forcing in this picture. There's going to be plenty of synoptic scale upward vertical motion through the mid part of the atmosphere. Moving down to the lower part of the atmosphere, now looking specifically at frontogenesis. This is within the 1,000 to 925 millibar layer. Cam highlighted it really well on his set of the presentation, but we had a set of frontal boundaries working into our states late on February 8th. And you can see specifically the cold front shows up very well by late afternoon on February 8th across western Wisconsin, southwest Wisconsin, northeast Iowa, and really kind of checks the box of, okay, we've got mid-level forcing on the synoptic scale, but we've also got low-level forcing. So it's very clear, synoptically speaking, on this day that there was going to be no shortage of upward vertical motion, really from the surface all the way up through the mid-levels of the atmosphere, which is something you obviously want to see for things like precipitation and thunderstorms. Having all of that synoptic scale lift is great, but ultimately if you're going to get thunderstorms, you got to have some sort of instability to work with. So I'm showing you a SQT here. I promise I won't throw you any ideal gas law equations or anything like that. You know, no one would appreciate that. They would call me a nerd. We don't want to do that. So we'll just keep it simple here. But from what you can remember from your thermo classes, there's two ways that we can destabilize the atmosphere, right? We can A, warm it from below, or on a SQT diagram, move that temperature trace over to the right in the lower half of the atmosphere. And or we can cool it from above, push that temperature line towards the left in the mid portions of the atmosphere. Either or of these, or both, depending on the day, is going to take that original parcel trace that you see there in brown and push it to the right. And of course, once we do that, we know that we are increasing that area between that parcel path and the surrounding environmental temperature profile. And as we know, the area between that parcel path and the surrounding environmental temperature is the CAPE. So you heat from below, cool from above, a little bit above, you're adding instability to the profile. So with that in mind, let's kind of take that and apply it to what we were seeing on February 8th. We showed you this image a couple slides ago, and with those basically clear skies moving in from Iowa, we knew that we were going to have plenty of surface heating going on. We had some early in the day, but we knew with this coming in the afternoon that we would have plenty more surface heating occurring. So we know we can check that box so that we were warming the atmosphere from below. But then also, with that trough coming in from the northern plains, so here I'm just showing you the 500 millibar heights a little closer to home, with the 500 millibar temperatures color-filled, you can tell that that trough, which was really embedded kind of within the northern jet stream, was bringing a cooler air mass aloft into the state as we moved into the afternoon hours. So not only were we heating the atmosphere from below across southern Wisconsin, we were also cooling it from above. So having both of these factors kind of in our back pocket, as we knew it would be going into the afternoon hours, it was unsurprising that we got some instability into the area. We're showing you the mixed layer CAPE at the same 4 time steps we've been working with. And you can see by late afternoon, early evening on February 8th, we had a weak but sufficient plume of instability of about 500 joules per kilogram across south central Wisconsin. So we knew that we had that synoptic scale lift, and because of the thermodynamics that were going on both near the surface and aloft in the atmosphere, we knew we were going to have that instability for thunderstorm activity. So then finally, we've checked all the boxes for synoptic scale forcing, instability for thunderstorms, but what are those thunderstorms going to look like? Are they going to be severe? Are they going to be garden variety? What would the hazards be if they do become severe? And really, the thing you want to be looking at when you're trying to diagnose this is wind shear. And in operations, we're tending to look at 2 different flavors of wind shear. You've got your speed wind shear. How is the wind speed changing with height in the atmosphere? You've also got your directional wind shear. How is the direction changing with height? And we like to look at both of these types of shear because they've got slightly different impacts on the morphology of storms, their behavior, the hazards that they might carry. Specifically with that speed shear, that's going to help kind of inform us of the ability for storms to organize. Are we going to just have garden variety thunderstorms? Are we going to have a QLCS, a line, maybe a supercell? That kind of will fall out of the puzzle with this. But then we also want to understand, okay, if we've got that speed shear to help storms organize, are we going to have that turning of the flow with height to support the rotation of thunderstorms and that threat for tornadoes? If we look at kind of how the near storm environment evolved here on the afternoon of February 8th, we'll start first on the right-hand side. In your interactive environments, you can see that you've got the 500 millibar trough coming in from the northern plains and a very strong jet of southwest flow aloft swinging through it. And really, it was that kind of southwesterly jet at the 500 millibar level that helped to enhance the speed shear, I should say, that we had in place over southern Wisconsin that afternoon. And that was well reflected in the effective shear that we had in place across the region. Numbers are a little hard to see in the back, so really that's about 35 to 45 knots of effective bulk shear that we had coming in to southern Wisconsin by late in the afternoon and the evening of February 8th. Plenty to help storms get organized for potential severe weather hazards. If we flip to the left-hand side of this and assess the directional component of the shear, at 850 millibars, kind of beneath this approaching trough from the plains, we had a very well-pronounced low-level jet that was moving into the region. And that low-level jet kind of took on more of a south-southwest orientation as opposed to the southwest orientation aloft. So that kind of gave us that turning action that we needed from the low levels up to the mid levels of the atmosphere to support rotating thunderstorms and potential tornadoes. In operations, we like to use a parameter called storm relative helicity to kind of quantify that. And we had anywhere between about 200 and 400 meters squared per second squared of SRH in the vicinity of these storms on the afternoon of February 8th, which is more than enough to support the potential for tornadoes. Unsurprisingly, with that directional and speed shear in place, by the time we got to 23Z here on February 8th, right about the time that the storms were about to produce tornadoes, it's unsurprising that because we have that directional shear, we've got an environment favorable for not just organized but potentially supercellular convection, which is clear on that supercell composite plot there on the right. But because we have that directional shear, not only could we have the potential for supercells, we could have the potential for tornadoes as well. So really, again, zooming back out to what we saw, because we knew that we were going to get that sunshine by late morning on February 8th, and we knew that that was going to be the kind of environment that we were going to be dealing with across our area by late afternoon, early evening on February 8th. And really, that was kind of what our life then became. Once we knew that, the rest of the day before we got into the warning phase of the event was really just spreading the messaging far and wide, making the public aware, making the media aware, making our EMs aware of the fact that something that was truly unprecedented might actually be in the works for the afternoon. And really, a lot of this messaging before we started issuing warnings revolved around just kind of simple graphics like this that we could make in 5-10 minutes at our workstations that sure highlighted the basic meteorology of what we were seeing, but also highlighted specific threat areas, hazard areas, and then how we were anticipating them to evolve over the near term. And we just kind of produced these graphics every 30 minutes, hour during that afternoon to almost give the public of southern Wisconsin a play-by-play of the things we were seeing. This is an example of one that we sent shortly after 11 o'clock in the morning on February 8th. We put this out on social media. We shared it in NWS chat, which is a screenshot that you see here. It's just the Slack channel. But really, we took these graphics and tried to spread them as far and wide as we could. This is just another example that we put out on Twitter and Facebook at about 1 o'clock. Again, highlighting the basic meteorology, the threats, and how we were expecting them to evolve. So that was really kind of what the afternoon leading up to this looked like. And now we kind of got into the warning phase of the event where we had storms on the radar and things were starting to evolve. So with that, I'll pass it to the man of the hour who was working the radar on February 8th, Kevin.
And apparently wearing the same outfit.
Yeah.
So we have the environment there. So now we have to actually move into radar ops. Kind of the meso, the environment is giving us that confidence that, hey, stuff is happening. So all those ingredients are there, so they're coming together, but we just need the storms to actually develop in the right area and see what happens. So now it's time to focus on radar. We get to look at that. So in operations, we had 2 great people on radar, myself and Michaela. Michaela is one of our new hires, and this was actually her first event working radar, and she got to issue her first severe thunderstorm warning during it. So kind of a hectic time once radar got going, but everything just kind of came together. It was just like Andrew and Cam talked about, these ingredients that we were looking at all came into place, and now we just needed to see what the storms did as they moved into the area. So next we're going to kind of just talk through the radar evolution of it, but first we're going to do a quick, brief radar lesson. Who here has ever heard of vertical side lobe contamination? So a handful of you guys. So this is actually a main factor in what happens. So this happens with radar. So if you all know, a lot of the stuff we go through in radar class is an idealized scenario, but there are just little flaws with the radar, and this is based off of the structure of the dome in there. So the beam sends out an energy, but there's some energy that gets a little bit above the beam and a little bit below the beam. And then when it hits a target, it can actually impact stuff in the main lobe of it and can kind of give you that false return, especially in the velocity signature. So this was one of the factors that we were dealing with the radar limitation for this event, and so we'll kind of mention that. But just want to give you a kind of a quick overview on that, because it played a role in our decision making when it came to it. So we saw storms kind of evolving upstream in Iowa, but as they started moving through, they didn't look all that impressive, but they were producing hail. We were getting reports. But as they crossed the Cheddar Curtain from Illinois into Wisconsin, you kind of start to see they kind of get their act together. Up here is just kind of a cluster we weren't worried about, but down here, these were getting a little more interesting. These are the ones that we're going to focus in on. So within that hour and a half, so this was about, let's see, time conversion, 22Z was 4. Yeah, 4 o'clock in the afternoon to about 5:30 in the afternoon. This is how the radar evolved. Again, we started looking at the storms as they're moving up. We're collaborating with our neighboring WFOs. The fun challenge about this area, it's actually the apex of where our office, the Davenport office, and the Chicago office all meet. So somewhere right over here. So we're talking with them, and I just remember on this day, as the storms are kind of crossing the border, Davenport's like, that's all yours, good luck with it, have fun with it. So yeah, 4 o'clock, things started to get going, mostly a hail threat. We did some initial severe thunderstorm warnings with it, but this concern started to grow. If you look over here in the velocity, you can see this consistent rotation signatures with these storms, especially with this little guy that's kind of moving out ahead of the main cluster here. You really can see that rotation there, and then even some stuff back there. So we're starting to see this rotation, and this was causing us some concern as we're kind of moving through. And then around 5 o'clock hour, that's really when things kind of started to ramp up across the border, and then just kind of kept going, and that's where it was just fast and furious with that one. So we'll kind of walk through it a little bit more in detail. So kind of the warning mindset as these two areas of concern move through. So again, we're kind of focusing in here's the Wisconsin-Illinois border right here. Before it crossed the border, we got 2 areas. So you can kind of see this is the half-degree tilt of velocity or storm relative velocity here, and then this is the radar feature. So reflectivity, it's not looking all that impressive at this time, but you've got these strong areas of rotation, and they persist as they kind of move across the border. So we're keeping an eye on it. Again, we have severe thunderstorm warnings out for it. So, and again, this is winter. This is early February. We're not used to seeing stuff like this happen. This isn't the deep south in February. This is Wisconsin in February. We haven't seen this. So we're seeing this, and then the one thing that's kind of causing us that iffy concern is that side lobe contamination stuff. So my main focus when we're kind of looking at this little guy out here, you have this rotation, but it just slightly offset from where the reflectivity is. So that was kind of giving us like, it's interesting, but we'll keep an eye on it, give it a few scans. As it persists, as it crosses the border, it's like, not liking how this is looking. You could start to see in reflectivity, you start to get higher reflectivities here, and you start to see that classic kidney bean shape of a supercell. Start to get that tail, it's like, and you're still seeing that rotation. Granted, on the half-degree scan, it's not as persistent, but you go up just a few scans, the 0.9 to 1.3, you really see that rotation persist. So with that persistent, or that persisting rotation, plus what we know about the environment, the meso-A. I had Andrew behind me kind of telling me what's going on, how the environment's going. Yeah, the environment's there. We're seeing a supercell, but we're also seeing that line, that little QLCS behind it. So it's like you have to take your forecast and you have to take what you're seeing. Granted, it's not looking the greatest, but you have to kind of believe in the environment that's there. Something can happen. And I also was getting concerned with, as these two storms kind of got close together, the QLCS was kind of moving more eastward, while this one was kind of moving more northward, so the potential of a merger was kind of growing concern. But you have to look at not just the lowest gain, you have to also look up in the environment. So again, this top of the hour wasn't liking this. 2 minutes later, it's like, yeah, the environment's there. And at this point, 1 minute later, I literally shouted out, it's like, y'all ready to make history?
That's the G-rated version of what he said, right? I'll go with that, yeah.
Because we never issued one. How do you do this? It's there, so you have to believe what you're seeing. And then you issue, at 1 minute later, it's like, all right, it's go time. We issued the first warning at 23:04Z, so about 5:04. Again, my main focus, you're kind of looking at the classic supercell shape. But you also can't ignore what's behind it. So that's kind of how it was. You had to have your eye on everything. That's kind of the challenge of being a radar operator. You're keeping an eye on everything going on. So my initial concern was this deviant, kind of almost left-moving supercell here, but you also had this QLCS that's just kind of moving towards it. And there was rotation in it. And so we ended up, a few minutes later, ended up going with another tornado warning behind it. Again, the side lobing, yes, it's slightly offset from where the reflectivity doesn't quite line up, but if you go up through height, it's persisting as you go up through the storm. So that was enough, plus the meso environment is giving us that confidence that we're going to issue this tornado warning. So it was the first one that we had in Wisconsin. So it's kind of nerve-wracking to kind of get the first one out there, but eventually it panned out. So kind of, again, we're diving into this one because this, I think the first Albany EF1 tornado was a little bit more interesting than the Evansville, but because of kind of this features. Again, that's vertical side lobe contamination. When you're on radar, again, my focus was on the initial supercell. So here's the example going through time. So this is about a quarter after the hour through the half hour. This area of concern, this is the half degree, seeing that broad rotation, and then it going here and here. At this time, as it was evolving, it was also merging with the line behind it. So that also adds more complexity to what's going on. So initially, again, focusing in on that, had the warning out, kind of fanned it out because of that. I anticipated that merger was happening and kind of seeing how that evolved. But in reality, one of the interesting things with this, the first tornado did not actually happen with the supercell out ahead. Because here, there's that rotation that we're keeping an eye with the main supercell. And then these dashed lines is actually where the damage path occurred with it. So in reality, so this is this velocity here. We actually had, this event was really weird as well because we had so many storm chasers on it, live chasing it. We're getting this information live, seeing how the storm is actually evolving on video. We don't even get that on our best severe days in the summer up here. So on February 8th, we had chasers out in the Albany one, and then we had so many photos coming in on the next one as well. So we're also getting these in as well, and you can kind of time match it. It just wasn't matching up. So we didn't really get the tornado until a little bit later, until you started to see this kind of interact with the QLCS. And with that, we were kind of focusing in on the secondary rotation kind of just to the south, which if you line that up with the radar or the reflectivity, it lines up more with that band behind it, the QLCS. So really, it kind of seems like it was more of a QLCS structure with this because it lines up closer to where the damage was. And with our spotters out, or chasers out there in live video, it matching up the time to our radar, that's where everything happened. So initially, we thought it was with the earlier one. People were reporting stuff from the Albany area, but because everyone it was rain-free bases, chasers were in the west looking east, kind of giving us this report. So they were reporting it from Albany when really it was kind of south of Albany. So all these reports coming in, plus the radar going on, really kind of helped solidify what we were doing in the warning process. And so as that one kind of went through, it was a pretty quick hitter one, as Cam kind of described. Things evolved. There was a brief lull after the half hour to about 5:40 in the afternoon, and then things changed. Went from a QLCS to a supercell to a full-blown supercell. So the modes have changed in the severe storm. So your thinking also has to evolve with it. So we're going from a quick little QLCS tornado to a full-blown plain supercell in February in Wisconsin. So looking at the timeline with this, we already had tornadoes, we had reports flying in from chasers. We even had Ben was out there kind of reporting damage, one of our observation program leaders.
Yeah.
So we're getting all these reports, all this information is flying in, keeping an eye on radar, and then, after the quarter of the hour, things really kind of start to ramp up. You start to see the tornado get that classic supercell feature, and then we also start to see the tornadic debris signature after it kind of moves through the Evansville area, and then we watch that kind of evolve through the top of the hour. So here's a loop of it, kind of how it evolved. And we'll kind of dive in a little bit more. The main thing with the Evansville one is pretty straightforward. It's a supercell. You can easily identify where that couplet is located. One of the key features, so just at the quarter hour, so we had that lull about 5 minutes before, but as things started ramping up, you start to see this feature, the donut hole on radar. We're about, I don't even know how far away, but you're shooting about 4,000 or 5,000 feet away from our radar over here, and you're seeing a donut hole. And then you look at the correlation coefficient, and you start to see that tornado debris signature develop. And this is what it looked like with height. So it's still pretty shallow. It's just moving kind of the southeast side of Evansville at this time. But once you start to see this tornado debris signature, that's when you kind of start to get concerned. Because that's indicating there's debris being lifted up by the tornado and being reflected back to us, letting us know that there's something on the ground. You have to have a lot of debris to kind of reflect that back. And through our damage survey, we identified it as a lot of sheet metals being flown around. So kind of the evolution of it, again, it's pretty straightforward. We had the tornado warning out with it. You can clearly see where that couplet is. But the big concern was this tornado debris signature. It kept growing. It got bigger in size and it kept growing in height. As a scientist, that's cool. As a person watching this and impacting people, it's scary. We knew people, our ITO at the time, his family is in the path of this. One of the forecasters from the Indianapolis office, his family is in Evansville, so it's like you have to also be grounded in understanding this is impacting people's lives. So it's nerve-wracking, but we got the warning out, so that was always kind of help with that. So, but again, reflectivity, velocity, pretty straightforward. You start to get a little bit rain-wrapped as you kind of move through time, but that tornado debris signature just continues. And by this time, it starts to grow with height. We're getting close. We're seeing debris being lofted up to 20,000 feet. And the higher that stuff goes, we'll show that here at the later slide, kind of gives you that estimate of how strong something may be. So it just continues, and it's just persistent. It's going through Evansville. It's starting to make its way towards Edgerton, and we're just continually getting these reports. The interesting thing about the Evansville versus Albany had reports from storm chasers, but these storms were hauling, so they quickly outran the storm chasers. But we got a lot of reports from the Evansville area of the general public and our spotters. A lot of pictures, like I believe there was one where somebody walked outside of a bar and took a picture and sent it to us.
That's not the most Wisconsin thing you'll ever see.
Yeah, right. So it's weird. We were getting these reports real time, so it really helped with what's going on. And then it just matched up with what we're seeing on radar. But again, it just continued through the top of the hour, and then eventually after the top of the hour, you start to weaken. Starts to weaken as it moves towards Lake Koshkonong. I think we had reports all the way up through Lake Koshkonong, and then as it moved into Fort Atkinson, that's when it really lost its legs.
It got tired.
Yeah. So
Might have used up the laughs on that one.
but here is the tornado debris signature. Looking at the vertical slice of it, you can see how it starts off kind of low and then just quickly goes up. It's kind of hard to capture this if you actually move just a little bit because it wasn't on a straight path, but it actually does get up to around 20,000 feet. And then looking at this chart over here, we had our rotation was somewhere between here. Our VROT was right just below 50 knots with that velocity couplet, and then the height around 20,000 feet. So that puts you somewhere in here. So it was clearly an EF2, nearing an EF3 level based on this study here. So fortunate for us, I think the path just kind of moved through part of town where there really wasn't as much as it could have hit, but if it, honestly, just 5 miles or even a mile difference could have been the difference.
Yeah, right.
So So yeah, it's the first historic tornado. We got a lot of media coverage with this one because not much was going on. It's historic. We got a national, local attention. The governor was keyed into this, what was going on. We actually sent out 3 survey teams. We had one on the Albany, started off there, and then we had one at the end of Evansville, and then we all kind of met in the middle. Andrew and our WCM, warning coordination meteorologist, Tim, they were the ones that kind of hit the ground at the worst part, and they dealt with a lot of the media. But it was a lot going on. There was a lot, actually quite a bit of damage. So here's an example of some of the pictures we actually took at. If this happened in summertime, this is the Albany tornado, the EF1. It actually moved through his campgrounds, Sweet Camp Mini Haha. It's right on the Sugar River outside of town. They had 100+ canoes that were gone. This one's embedded in the camp, and we found some of these canoes about half a mile down the road. So it would have went through a campground. It rolled trailers. It impacted. This is the camp owner's home that was peeled back. This is most of this damage looks worse than it is. It's actually a prefab home that had poor construction. The walls were glued on, no nails or anything. So you had a chicken coop hit it and peeled it back. So it did produce quite a bit of damage, but it was only EF1 damage. But it still thrown boards into ceilings and stuff like that. This was a brand new garage that was just completely wiped off. But again, it was mostly, they had good anchoring with it. The main concern with that one is the wind caught it, and at the garage door is a fail point and just kind of blew it down. Because you could see all the content inside was fine. Evansville, Lake Koshkonong, that one much stronger. You can see the video here. We have lots of video of it developing before it got rain wrapped. It's actually really kind of, the videos are just amazing, I think. So you go to our story map, all those are on there. Yeah. But the damage path, it's running a marathon worth of damage. So you're toppling trailers, pulling roofs off, throwing them down. Doesn't look all that impressive until you realize this tree was thrown and embedded into the ground. It's not where it originally was.
Yeah, it's not uprooted. That's like the top half of a tree that was sawed and then just thrown into the ground, basically.
So you just saw this. You saw this damage path for pretty much from the start of Evansville all the way through Lake Koshkonong, and it started to broaden out as you got towards Koshkonong with it. So, and it mattered. Our warnings mattered. We had a family this is their home after the Evansville. They got the warning. They were sitting down at the table right there, right, for dinner.
Yeah, that was their kitchen, basically.
Yeah.
So
they got the warning, went to the basement, and they were safe.
Yeah.
Miraculously, we had one injury from a storm chaser from this.
One injury. Yeah.
Otherwise, the only other fatality that we know was a cow or something.
Yeah.
So people got the word. People knew it was out there, and yeah, it's just crazy that it didn't have more for a high-end EF2 because we were considering maybe going above.
Yeah, but it was a success story. You don't always get the success stories, but this is one of them. So it's nice to share it and kind of see how it can all work. So.
And it was a success because it was a combination. We had the idea of what's going on. We had the idea of what we needed to look for in the forecast, what ifs needed to come together for us to get this, the in-depth meso-analysis at the surf or the couple hours leading up to it, getting that message out, letting our partners know around the noon time. So they had about 4 or 5 hours of lead time, kind of heads up that this is, hey, we're actually seeing this. Very, very low chance of happening is actually happening. And then actually trusting the environment, going with radar, understanding the radar, looking up at height, knowing the flaws, but also knowing the environment that can help kind of lead you to it. And yeah, it's Midwest weather. It's challenging, but overall, I think it's a unique event. We've never had a February tornado in recorded history. So, that goes back to 1950, and even the book that goes back into the 1850s.
Mm-hmm.
So,
crazy event.
Definitely a unique event. But with that, we'll take any questions. Yeah.
There you go. John?
I'm going to break our rules. Usually students are going to run in a minute. It's not so much a question as a comment, with a question at the end. The comment is, this is the best example I think I've ever seen of how, when you're learning about any kind of weather phenomenon, and I think it's especially true for severe weather, one has to get past the checklist. sort of mentality. Are all these things happening? And I check them off the list, and then I issue a warning, or I have a suspicion that something's going to happen. This was vigilance by experts, paying attention to every scale and making sure that everything was kind of coming together, and being hesitant because of the somewhat historical nature, the unprecedented nature of it. I think it's fantastic. So my question is, has anybody nominated you guys for the AMS specific excellent forecast? Because that would be something.
Not to our knowledge. No, I guess we'll find out.
I
but
think
not
this
to our
would be a
knowledge, no.
perfect case for that, because not only the impacts, but also because of the nature in which the warning mentality evolved during the day, as you carefully laid out for us. I think it's a stunning success story for the importance of training expert scientists and then putting them in charge of making forecasts. And I guess my other question is, we're at the dawn of the AI era. I'm almost certain, sitting here right now, that AI would not have contributed anything more to this forecast than your expertise.
Yeah, I mean, the AI is going to be a tool. It's going to be coming, and it's going to be here as a tool. But at the end of the day, you still need to communicate whatever the AI might be showing you, along with the physical models and all of that. So, I always tell students that there's going to be a role for the forecaster in the future of whether the tools that we use may evolve, they might change. But at the end of the day, end A to end B in terms of talking to your partners, talking to the public, that's never going away. So there's always going to be that
There
part
needs
of
to be
it.
a liaison.
Yeah.
It's just excellent.
Yeah.
Great story. Thanks for coming to tell us.
The messaging side, I think, that's where the NWS is going, is working with their partners, letting them know that this complicated setup, kind of giving them that information that they need to make the best decisions. Even if it's not a deterministic forecast, we can give them the scenarios, the outcomes of it. Because I don't know how AI would handle sideload contamination.
Yeah.
We had that tornado vortex signature algorithm that always has outflows too.
Yeah.
So I don't know, AI is probably smarter than that now.
If you're
but-
training something on images,
Yeah.
it sees that couplet, it's going to be like, oh, that couplet, even though it's side loading.
Yeah.
There's just
Yeah.
that part of it. There's
Yeah.
the fact that this has never happened before. So you can only train AI on data that's out there, and there were no data points on this, at least here in Wisconsin. So the odds that it would even point to that probably would have never been a thing. So the role of the human's always going to be there, no matter the tool.
Great story.
Yeah. Yeah.
I got two questions.
Yeah.
First one being, you noted that there was no snow cover, which is pretty odd for February.
Yeah.
Do you think that the change in surface friction had a impact on how much low-level wind shear you saw in this case? And potentially, if there was snow cover, do you think that EF1 might have just been eliminated?
That's interesting. That's honestly something I hadn't thought about in this case, and goes to show you, it just keeps getting more interesting. I mean, it's definitely something to think about. That would probably be something that you would have to replicate, with a numerical simulation in terms of the storm, and do it with and without snowpack. But it's certainly something I can't discount, given the factors that you note there. I think if we had a snowpack, we wouldn't have been anywhere in the realm even of potentially looking at thunderstorms on this day either. That was a huge part of it. And it wasn't just the snowpack in Wisconsin. The snowpack regionally was just non-existent at that point in February. You had to go pretty much up into Canada to see it. So I definitely think that impacts things in terms of storm tracks and all of that, in terms of how far south is our snowpack in the wintertime. So definitely roles to be played by it, both on the kind of very, very small scale as well as the broader scale.
Gotcha. And
Yeah.
then the second question was, do you have any idea of what the SIG-core values were? And if it breaks climatology?
Yeah, so I mean, our climatology was non-existent. So at the beginning of the presentation, we kind of had a slide. It was based on some SPC climatology work that had been done. The data set ends at 2011, but basically goes through the year, takes a 3-week centered average on every week, gets a climatology for that. And I mean, the data was non-existent, really, 0.1% contours only came up to southern Illinois. So we basically had to do a little bit of extrapolation because we were, kind of in that realm of this just doesn't exist. So how can we contextualize it in terms of numbers? So in terms of values, we were between 1 and 2 on the SIG tour that day. Limited by the instability. I mean, we only had 500 joules of CAPE around that day, but it was enough, with all the dynamics that we had to play for tornadoes. So it was right in there, and I would bet for February 8th, that's probably the highest you're going to see for a long, long time around here. Yeah.
So I want to bring it back to the AI discussion,
Yeah.
because you guys kind of said it's up and coming, but I would argue with you that it's already here. And there are AI models that are in operations right now, like Severe, that can be used for these sorts of things. So my we do better when we're making these sorts of models that would help you kind of actually use some of the materials we're developing?
Well, we do have them, yes.
Yeah, we were using props of
Yeah.
We were using it.
So,
and it performed pretty well,
Yeah.
honestly, in this case. The thing in operations, you have to calibrate. So you might see a day where you have a 30% probability on prob severe, and a 30% probability, that's not going to be made equally between the warm season and the cool season. So on a day like February 8th, 30% is off the charts, and internally you're kind of thinking, okay, like this is way higher than what we need to have the confidence in the warning decisions that we're making. So it definitely played a part, I mean, with the environmental analysis, with the numerical weather prediction, and then once storms started popping up on the radar, things like lightning cast, we could tell storms were intensifying over northeast Illinois because of some of the lightning algorithms that were telling us that the lightning was going up. But then things like prob hail, and then, I mean, obviously prob torb when the tornado was in progress was just going nuts. So it definitely factored in. I wasn't making the warning decisions, but I feel like
Yeah,
it was there.
I have it up all the time. It's
Yeah.
on my radar procedure.
Yeah.
Marcia's husband works with it, so we kind of got an early taste of it.
Yeah.
So we use it. Yeah, it's another tool that we have.
Right. We're not like making warning decisions purely on prob severe, but it's another tool in the tool chest,
Yeah, a
basically.
little nudger.
Yeah.
So we have the environment, we have the radar. That's just another check that we can check off the list. That kind of like, well, it says it, so helps us with it. So, yeah, we're trying to incorporate new technology. It comes at this rate. It's coming out so fast. It's
Yeah.
really, it is challenging.
Well, and beyond prob severe, I mean, there's stuff going on with severe weather prediction, hurricane prediction,
Yeah.
that's using, artificial intelligence. That's
The
a
war
little
on.
further behind and more just in the trial stages right now. But
Warn on forecast.
yeah, warn on forecast. So there's tools that have made it into ops, and then there's tools that are on the cusp of getting into ops, and
So
it's.
then my kind of follow-up question for you is there anything that stuck out to you with this case that you thought, oh man, we wish we had this? Because a lot of us are on the research side, we're in SIMS, we have kind of that operational kind of research to operations mentality. So was there anything else you could think of that maybe you could have thought would be helpful to have going forward?
So I think you start to get into, it's kind of a double-edged sword, where you have almost too much information. So really it is, I don't know if there's necessarily anything that I would have required more other than probably more radars.
That would have been nice to have a WAFs run. WAFs is
Yeah.
situational, so I mean, WAFs is, it's there, but the decision to run it is completely out of our hands
Yeah,
in the
right.
field. It's made essentially at NWS HQ and SPC, right? And there's a strict threshold of enhanced risk or nothing, basically. So, if there's not an enhanced risk, that's a non-starter on WAFs. And then even when it does run, take a day like today where there's an enhanced risk over Kansas and we only have a marginal risk. They've got to make targeted choices with where they put that domain. So even on a day, if you had it, you might not be in it. Like on a day like today, we'd either be on the far northern edge of that domain or not in it at all. But I think hypothetically, perfect world, it would have been cool to see what WAFs did with a case like this, because the HER was hit and miss, honestly. I mean, we were kind of going old school forecasting with it, just trusting the environment and everything that we had there.
That's what we normally do in Wisconsin.
Yeah, no, exactly. So I feel like WAFs would have been interesting to at least evaluate on a case like this to see how it handled that environment, because it's just looking at the science, it's not looking at the history of any other part of it. So that would have been an interesting thing.
Yeah,
I'd say.
on the research side, just give us more computational power. That's what we need.
Yeah.
Yeah.
Right, thanks guys.
Yeah.
Turning to the communication side, so it's refreshing to hear a success story of a synergistic two-way communication of storm reports and sending out awareness to the public of an unprecedented event. I'm curious to hear, are there any lessons that you pull from anything that could have been done differently in like the interface of communication with storm reports or between field offices or any lessons that were learned in terms of communication?
Yeah.
I'll take that one.
Okay. I have a knee-jerk answer, but yours is probably going to be better, so I'll let you go first.
So really with the messaging, it is a buildup of a relationship. We've been working on building up this relationship with our partners. So that includes emergency management, local community decision makers, the state of Wisconsin. We're the state liaison office, so we work with the Wisconsin Emergency Management. So having that relationship ahead of time, you don't want to build that relationship as this is going on. You want to have that relationship so they know they can trust you. They have that information. They can make the decision. Even if we're not saying, hey, this has definitely happened, we can at least give them that. They trust us enough to know that, hey, this is the scenario. We'll prepare, maybe start the ball rolling for something to happen, and then when it does happen, we give that information. They can hit the ground running with it.
Yeah.
From that aspect, the messaging, yeah, it's a trust. We sent out an email, around noon that day.
Yeah.
So all our partners that we built that relationship with got that information. Our partners on NWS chat, so the media partners, they're getting this information. They can get it out to the people. They can put it on their social medias. We put it on our social medias. So you really have to build that network and build a network of trust to get that information out. As for the collaboration side of things, it's, is that what you were going to kind of talk about?
No, it's something totally different. So
Yeah.
keep going.
Okay.
You're doing
But yeah,
great.
collaboration, it's, again, trust with your neighbors. That is one of I will say it is a challenge doing the forecast. You have a lot of smart people in the National Weather Service. They all sometimes don't agree on the forecast. But it really is like kind of, that day we actually had a pretty good agreement with the Chicago office, Davenport office, La Crosse office, and us, kind of understanding the environment. We recognize locally. We're the experts around the Great Lakes. So yeah, it's really just kind of build it up with your partners and trust them.
Yeah. I was just gonna say too, like one thing we kind of took out of this too is that this day we didn't have a particular watch, but we, on a general day where we have severe weather, we bridge the gap between the watch and the warning. So, we really learned, especially like getting the events, like the updates out, like with the Meso-A. Like we did all of that stuff on our own prompting. So like those little graphics that you saw where I think Quigley put them together, where basically highlighting radar and saying this corridor here is under the risk for a tornado over the next like hour or two, based upon what the storm is doing. Like that's one thing that we took away from this, is that we can do that on our own. We don't have to wait for the SPC to put out a mesoscale discussion. We can do that on our own to supplement the information that's going out there. So I think that's a big thing that we took away.
Yeah, I don't have anything to add other than the fact that if you send us videos, just try not to swear. Like we got so many videos of this tornado, and it's like giving us spotter talk content for years, but like every single one is like, oh, boom, 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 oh my God, look at that, boom. Like, I mean,
We just mute them. But sending videos, our spotters were truly helpful in the Evansville area, kind of giving us that information. The storm chasers and some spotters in Albany, they were on the ground giving us this information as quickly as we can.
Yeah.
If there's a live chaser feed and there's a storm, we'll pull it up. It gives us something else to look at. It's another tool. So any information is good.
Any other questions? All right. Well, thank you guys for coming. We really appreciate you coming up to listen. So.
Or your charger.
Yeah, no, exactly. And then we did do a story map. Just one last thing. We did a story map. If you want to see it, check it out. You can scan the QR code there. It's also on our website, the National Weather Service page.